If we wanted to study earthquakes and the way that those energy waves move, we would be studying seismology. But we want to be able to be kind of precise when we're talking about how much the ground is moving due to these energy waves. So we want to be able to measure their energy. And we do this with a device that's called a seismometer. And you can see it in this image. A seismometer is a device that is drilled and connected deep into the bedrock underneath the surface. We wouldn't want this to just be sitting along the surface because common things like a large truck going by, an airplane flying over, can cause the surface of our planet to shake a little bit. But when we're studying earthquakes, we only want to measure the earthquakes. We don't care about the planes, trains, and buses nearby. So we're going to drill this seismometer really deep into the earth so it will only measure the earth itself moving, not everything moving around the surface. But when an earthquake actually happens and it causes deep underground to start shaking back and forth, on the surface, this seismometer has a little arm that sticks out to the side. And along this arm, it's going to have a pin that drops down and is going to swing back and forth over a rotating drum of paper. And here, if we just have a little bit of shaking, it's just going to move back and forth a little bit. But if we have a whole lot of shaking, it's going to move back and forth a lot, creating larger or higher amplitude waves. So when we have the data that's already drawn out by this seismometer, the data itself is called a seismogram. When we look at these seismic waves, or these energy waves that are released once we suddenly have slippage or rupture, creating an earthquake, these seismic waves are going to move in two different ways. One type is called a surface wave, and this is where these seismic waves, or the energy rays, travel just below the surface of Earth and the very uppermost rocks, very close to where we live. But the second type of seismic wave is called a body wave, and these do not just travel near the surface, but instead they travel through the interior of Earth's body. It moves through the not quite the center, but throughout the interior of our Earth. Looking at our body waves, or the ones that are moving through Earth's interior, we have two types. And these are our primary, which we call our P waves, or the secondary, the S waves. And we're going to see that when we are looking at our seismograms, that they arrive in different orders. Our primary waves arrive first. They travel faster, and our secondary waves arrive second. They travel a little bit slower. But we're going to see that they have different arrival times because they move in different ways inside of the Earth. With our P waves, or our primary or first wave, this is where the rocks are going to be pushed and pulled in whichever direction the wave is traveling. And to be honest, I don't think that makes a whole lot of sense. But what does is playing with a slinky. So here, if we look at this diagram, I can pull out this slinky and then I can push it back together. Here, I'm pushing and pulling in the direction of a wave, whichever way my hand is moving. And this is exactly how our primary waves move through the Earth. They're capable of changing the volume of the material by pushing and pulling it, by compressing and pulling it backwards. And because it's changing the volume, these P waves can travel through all types of matter. They can travel through solids, liquids, and gases because it's changing the volume, or how much space it's taking up. Our secondary, or S waves, are the ones that show up second on the seismogram. And these move totally different than our P waves. These S waves are moving at right angles to the direction they're traveling. And again, just saying that doesn't make a lot of sense. But think about those ropes that you'll see in the gym, where the trainer will have you pick them up and slam them back on the ground. This is exactly how our S waves move. They're moving at right angles. It's waves moving up and down as the energy is traveling through that rope or the wave. So here with these S waves, we're not changing the volume like we were with the P waves. Instead, we're changing the shape of the material. We're causing it to move up and down as we send energy through it. And we can't change the shape of a liquid or a gas because it always just takes up the shape that it's in. So because of this, our S waves cannot travel through liquids or gases. And this is going to be an issue when it's traveling through Earth's core, which is a rotating ball of liquid magma. Looking at our surface waves, though, not body waves, our surface waves only travel near the surface. They don't go through Earth's interior. We'll have two types of surface waves, just like we had two types of body waves. And here with our surface waves, they're either going to move up and down. It's going to be like wave motion in our oceans. If you've ever been at the beach and you stood in the water, the waves will push you up and down. This is one way that our seismic waves can move through the surface. But the second type is not where the ground is moving up and down, but instead it's moving side to side. And here, this is the most damaging type of ground motion because it's going to be breaking apart our roads. It's going to destroy parking lots and buildings instead of just having them move up and down. But when we look at our seismogram, or the actual data that's being recorded by the seismometer, the device that's recording the earthquake, we'll notice that each of these waves arrive at different times. We start reading our seismogram from the left and then read towards the right. So you'll notice that on the very left, it's a very straight line. But here, it starts moving up and down a little bit. The moment that it goes from a straight line and starts moving upwards, this is our primary, or our P wave. It always arrives first, which is why it's called primary. But after the P wave hits, after a few little oscillations moving back and forth, it's going to kind of flatten out again. It's not quite as even as it was before because the earthquake is still going on. We've just had the first wave hit us. But after our primary wave, our secondary wave is going to hit. So here we'll see that once again, that seismogram suddenly juts upwards. That's exactly when our S wave arrives. And then over time, it's going to get a little bit flatter. But then finally, our last wave to arrive is our surface wave. These are the ones that travel through the surface, so they'll have to travel a longer distance to reach the destination, and it will take them longer to arrive. We'll always see that they will arrive in this order: primary, secondary, and then surface waves. But you'll see that the amplitude or the height of each of these waves changes as well. And they increase so that P waves have the shortest, then S waves, and then our surface waves have the highest amplitude or the largest change in their waves. This is telling us that the greatest amount of shaking is occurring when these surface waves arrive, not our body waves, the P and S waves.